Hello everyone, today I am presenting Codebase Agent, hardening an enterprise knowledge server across evolving runtimes. What began as an intensive capstone project quickly became a systems engineering challenge. The goal? Eliminate framework and OS bottlenecks to achieve production grade, low latency code comprehension at scale. Building a mental model of a massive code base is a crushing cognitive burden. Why? Because traditional search and raw LLMs cannot trace nonlinear multi-file execution chains. My project bridges this gap by transforming static repositories into interactive deterministic knowledge server that provides an instant architectural blueprint. Why agents for code comprehension? Single shot track completely fails here because code bases are nonlinear dependency graphs, not flat text files. Answering a basic onboarding question requires recursive multi-step execution. Built on the Google ADK, this agent acts as a stateful engine, breaking the query into sequential steps, evaluating intermediate tool outputs, and rewriting its execution plan mid-flight. To systematically benchmark performance, I decoupled the system into a data versus compute paradigm. The data layer is the universal constant, combining semantic ChromaDB embeddings with a structural NetworkX call graph. With data fixed, the compute runtime becomes our testing variable. This allowed me to track structural evolution from isolated workers of version 0 to modular skills in version 1, and finally to a persistent native MCP server of version 2. This engineering journey eliminated bottlenecks across three distinct runtime phases. In phase 0, developed in November 2025, I built a traditional multi-agent hierarchy. A central Google ADK manager orchestrated specialized search and graph agents. But token serialization chatter across those agent boundaries created a severe framework tax, driving latency to 83 seconds. Phase 1 collapsed this topology into a single ADK agent using standalone agent skills. This successfully eliminated agent-to-agent chat overhead, dropping latency to 24 seconds. However, it unmasked an OS-level subprocess tax, ephemeral tool turns, forced cold disk reads, and library reimports from scratch. This culminated in Phase 2. I kept the single agent loop, but backed it with a persistent native MCP background server. The server loads both NetworkX call graph and ChromaDB embeddings into hot system memory exactly once upon boot. This transforms heavy IO into instant object reference lookups, resolving complex execution graphs in just 3.5 seconds. For my demo, I ran a complex query to trace a multi-file document processing pipeline. Traditional RAG fails here, but the agent immediately enters a planned React loop to map a strict multi-step execution plan. Turn 1 invokes the code semantic search MCP tool to pinpoint create RAG chain as our entry point. Turn 2 dynamically pivots to code graph inspection MCP tool, traversing the call tree to isolate scrape site and vector retriever methods. It climbs down the syntax tree, capturing exactly how data flows from sitemap parsing down to chunk splitting and local ChromaDB persistence. Finally, it synthesizes these tool turns into a deterministic architectural blueprint. With the background MCP daemon pinning these indices in hot RAM, the graph resolves near instantly. Architecturally, I maximized the Google ecosystem using Google ADK, Gemini models, anti-gravity CLI, and Kaggle. To wrap up, eliminating framework and IO bottlenecks yielded a 23x performance leap, compressing latency down to 3.5 seconds. The takeaway? Massive code bases require persistent background runtimes, not ephemeral tools. Next phase is Git automation. The system is fully open sourced on Kaggle. Thank you.